Why is freezing in solutions more complex than pure substances? Have you ever wondered why freezing a solution is not as straightforward as freezing pure water? It turns out the presence of solute particles makes a big difference. Let's break this down in a simple way. When we think about pure substances, like water, they freeze at a specific temperature. This temperature is where the liquid and solid forms of the substance are balanced. For water, that freezing point is 0 degrees Celsius. At this point, the energy states of the liquid and solid are equal, allowing for a smooth transition from liquid to solid. Now, when we add solutes, such as salt or sugar, to the water, we create a solution. The solute particles disrupt the neat arrangement of water molecules that need to come together to form ice. This disruption means that the water cannot freeze at the usual 0 degrees Celsius anymore. Instead, the freezing point drops, which is known as freezing point depression. The extent of this freezing point depression depends on how many solute particles are in the solution, not what those particles are. This is a property called colligative property. For instance, when you add salt to water, it lowers the freezing point more than if you added the same amount of sugar. This happens because salt breaks down into multiple ions in the solution, increasing the number of particles. To quantify this change, there is a mathematical relationship that shows how the freezing point changes based on the concentration of solute particles. The change in freezing point is proportional to the molal concentration of the solute and a specific constant for the solvent. This relationship also includes a factor that accounts for how many particles a solute creates in solution. Solutions can also have unique characteristics, like a eutectic point. This is a specific combination of solute and solvent that freezes at a lower temperature than either component alone. This means that the freezing behavior of solutions is not just a single temperature but can vary widely based on the concentration and type of solute present. In practical terms, this complexity explains why seawater freezes at temperatures below 0 degrees Celsius. It also explains why we use salt to melt ice on roads during winter. The salt lowers the freezing point of the water, preventing it from solidifying. Similarly, antifreeze solutions in car engines work by lowering the freezing point of the coolant, ensuring the engine does not freeze in cold weather. So, freezing in solutions is more complex than in pure substances because solute particles change how the freezing process works. They requiring lower temperatures to freeze and make the freezing point dependent on the concentration and type of solute, rather than being a fixed temperature as with pure substances.